Okay, it looks like we're recording, so we're gonna go ahead and get started. Remember our drag force equation from yesterday, and we talked at the beginning of the class that this is proportional to the velocity squared. When you're taking your AP test, a lot of times you're going to see that relationship simplified. All right, and so that relationship is actually going to look like this. So you'll notice that your drag force is equal to some like coefficient. Typically they call it beta, but it might be something other than beta. Is equal or multiplied times b squared. And one of the questions that you're going to be asked frequently on your AP test, you'll see at least one of them, if not more of them, is you're going to be asked to write a differential equation. And when you write the differential equation, the wording is going to give you a clue on how to solve the problem. So this is some example wording that you will see. So it will ask you to write a differential equation for the velocity of an object as a function of time. Okay? So what you'll need to do for yourself is you're going to need to translate that into English, because that's like, I don't know what that is, right? So we're going to translate that into English. And to translate that into English, easiest way to do that is to break it down into parts. I'm just making my marker smaller so it's not so hard to read. Okay, so when we see the words differential equation, what that means is you're going to have d something divided by d something. So an example of the differential would be like dx dt. All right, what does dx dt mean? Is a derivative of the position function, position with a function of time, and what is this equal to? The velocity. Yeah, good man. So it's the velocity. And so when they're asking you to write a differential equation, you're going to have some sort of equation that has this sort of statement in it. But the College Board will actually give you what these variables are right here and right here in the question itself. Okay? So the next step that I think is helpful is identifying those two things, right? So if you read further, what are the two variables that they're asking you to write the differential equation for? Yeah, your velocity and your time. So they're really asking you to write dv dt. Now I know that's not an equation, right? That's just like fraction, right? Derivative, the derivative of the differential of velocity divided by that differential of time. So we've got these little itty bitty bits of velocity at a given time. What is that equal to? This is your acceleration. Okay, so let's kind of zoom out for a second and look big picture. We've been talking about and drawing force diagrams for an object falling in free fall with a drag force. Okay, you're following me so far? And I need to write a differential equation that has something in it that's going to be dv dt, and we know that's equal to an acceleration. What does that like lead you to think you need to do? Yes, but we got to go one step back. For those of you watching at home, I'm awkwardly drinking out of my mug, right? We have to sum our forces. So if we have our skydiver up there in our corner, right? Our skydiver up there, what force or forces is that skydiver feeling?
Gravity.
All right, so we have a gravitational force, and we have a drag force. And that drag force, that varies over time, depending on how fast the object or that skydiver is going. All right, so what I'd like you to do is, if you're watching at home, go ahead and pause the video for a second. You guys here, I'd like you to write your differential equation. Translation. Sum your forces for the skydiver. All right, what did we get for our sum? Okay, so you said f of d minus fg. Oh, okay. MA. So Spencer actually flipped those because he flipped his axis system, right? You flipped your axis system. You could do that either way. I did not write an axis system on my course diagram, so I guess I assumed a traditional axis system, but you certainly could do that. Okay? So there's step one. Now we need to make this, because this is just a plain sum, this isn't a differential equation. So I think it's pretty clear what we can do right to make this a differential equation. I think so. Yeah, somebody's coughing and hawing. Yeah.
Would you solve for like A on the other side? So like you divide your forces by mass and you plug in for A.
We don't even really have to go that far. Really what we need to do is we just need to take this and sub it in there. Yeah, we need to take that and sub it in there. And then we also need to drill down a little bit more on these because my entire differential equation needs to be in terms of velocity and time and then constants. Right? When we're writing a differential equation, we need to have velocity in it, we need to have time in it, and we need to have constants and no other variables. So see, our FD and our FG are other variables. So we need to start substituting some other things in too. Okay, so we know our drag force is this beta times velocity squared, so let's go ahead and sub that in. That constant times velocity squared minus, and then FG we know is just mg. And then that's equal to m, and then we replace the a with the dv dt. Yay! We did it!
Alphabet soup.
Alphabet soup! We just wrote a differential equation. Okay, so this is what you're being asked for when you're being asked for a differential equation. Yeah?
Do they care what the mass is?
No, actually they will not care. They just need an equation that's in the following terms. It needs to have velocity in it, needs to have time in it, and the other values that are in there need to be constants. So for instance, your beta there, that's a constant for that particular situation, as is mass and g. Right? Those are going to be constants that are given to you in that system. And the only variables, the only things that can be changing are the two that are in your differential, the dv dt. When we get a little more calculus under our belt, we're going to learn how to separate those variables, and then we're going to integrate that function, and then we'll actually get a function of how velocity varies with time. And we're going to see that that's going to look a lot like what we did yesterday with our terminal velocity. We just aren't quite there in terms of math, and I find that it works a little bit better if you guys have a little bit more before I try to shove that in your brain. Okay? Questions to there?